work again today? Seems it does. Cinnamon ruby is quite good. Cinnamon. Cool. That sounds really good. Yeah, cinnamon rolls also goes well with tea with mint leaves. Now I'm hungry. I don't know how I'm gonna continue with teaching the lecture today, now that we're talking about tea and cinnamon and mint leaves and so on. Maybe after class. Alright, so where are we today? So in today's lecture we are going to talk about inter-procedural analysis. So now we're going to cross the method boundaries. But before we do so, let's have a quick refresh of our previous lectures. So in our previous lectures, not just the one on Tuesday, but also the lectures before then, we talked a little bit about not a little bit, we talked about points to analyses and pointer analysis, aliases and what aliases means, and alias analysis. We've also talked about two main variations of analyses depending on the kind of information that they provide. One is a must analysis, one is a may analysis. The differences between them is that a must analysis is typically an analysis that is flow sensitive, so you can say for sure, or you have sort of a guarantee about the analysis result with respect to the ordering of the statements of the program. May analysis, on the other hand, is typically flow insensitive, so you just treat the list or the sequence of statements as a set rather than a sequence in your program. So you cannot say anything for sure because it does not respect the control flow of the program. We talked a little bit about how an alias analysis might be more suitable for computing certain analysis results for incomplete programs versus pointer analysis, where you cannot, for example, analyze parts of the program like library calls because you don't have that information, or you do not rather want to analyze those library dependencies. We've also talked about weak updates versus strong updates and how must analyses allow you to eventually do strong updates if you want, which is killing old information or stale information and moving on with new information. Weak updates, you just keep adding and piling up information as you go so you don't forget old information. Access paths and how we can use them as object descriptors and how that sort of allows us to easily identify aliases and also have descriptive labels for objects that we are going to use and propagate in our data flow functions. We very briefly talked about distributivity towards the end of the lecture last time, but we're going to talk about it more at length when we start talking about IFDS in about a week from today. In today's lecture, we are going to start now to combine all the information that we have had. I'm realizing that I have my wrong mic on, so just realized that. So please tell me if this now sounds better than before. All right, cool. Yeah, I had my Rode mic on, but I didn't have it selected in the stream and on Twitch and on Zoom. So yeah, cool. So moving on, now that we have a better mic. So now we are going to combine the analyses that we have, the intra-procedural algorithms that we've discussed towards the beginning of our course, on top of the call graph analyses and the call graph construction algorithms that we have discussed in last week, such that we can have an analysis that crosses method boundaries. So we're going beyond method boundaries now. Typically, an inter-procedural analysis would model the workflow, would model the effect of two things. One is the calls and the calls in the caller, so the call sites that you find in caller methods. So if you have method foo, and in method foo you have a call to method bar, and maybe there's some code here, some code there. So we're going to track calls in callers, and we're going to track one other important piece of information, which is the calling context in the callees. So we're going to track calls in callers, and we're going to track calling contexts in callees. There are multiple approaches to inter-procedural data flow analysis. Generic approaches include call strings approach, which we're going to discuss next Tuesday. Functional approach, again, we're going to discuss that next Tuesday when we talk about context sensitivity. Some are a bit more problem specific, such as alias analysis. This is an inter-procedural analysis because you want to know aliases throughout your whole program. Points to analysis, same thing. Partial redundancy elimination, so figuring out common sub-expressions that you can eliminate in your program so that you don't have to repeat computations. Constant propagation, we have seen this example many times in the course so far. So as an example, let's just look or have a look here at this piece of code. So in this piece of code here we have three functions: function S, function R, and function T. And so how do we actually perform this inter-procedural data flow analysis? So you have three functions and you want to cross those method boundaries. So the first thing we're going to do is we're going to enhance the control flow graph for each method with a few more nodes. So we're going to sprinkle some nodes on the control flow graphs of those methods to see how we can combine them together. So for each method, we're going to have a starting node. So S, starting of R, starting of T. We're also going to have an end node, end S, end R, and end T. So these are additional nodes in the control flow graphs. And basically in between those nodes, we're going to just put in the nodes in, we're going also to add additionally nodes for the call sites that we're going to have. So let's say here you have a call site outline I. So once that call site is reached, we're going to add an edge to the starting point of the method we're calling. We're going to have the control flow graph in this dotted line here for that method. And then once the method ends, we're going to join that end node to the return point of that call site. So every call site now will be represented by, or every method call in your program will be represented by two nodes. A call node that happens at the call, then the return node, which is the return right after the call. And we're going to have this pair of nodes for every single call site in our program. And basically what we're going to do is, along those edges, we're going to say, well, here I'm going to pass x as a parameter, so it's going here as x. Then we have the function that represents R. Remember, the monotone framework, the function composition of all the flow functions along the paths of that method. That would be basically our method summary in this case, is going to be applied to x. And the output of that function is going to be x bar or x prime, and this is going to be returned to the return side. So this is my return. So basically x prime will be the application of the function fr on the argument of the function x at this point. All right, so there are two types of facts that these functions or an inter-procedural analysis deals with. There are inherited facts. So these are the facts that every node or every method will inherit from the incoming context. And there are the synthesized facts. So these are the output facts. So basically these are input facts and these are output facts. To use terminology that we have used in the lectures before, these would be the V in, right? And these would be your V outs, basically. We're going to do the same thing for other call sites that we have in our program. So here we have function T, we have CJ, another call site. So we're going to mark this with a pair of nodes. One for the call site and the other one for the return. It's calling R, so we're going to join this or connect CJ to SR. We're going to connect ER to RJ, and the idea now is if you pass this a different value Y from that call site, so this is going to be passed here, you're going to get back Y prime which is the result of applying the function fr, the same function fr, but to a different argument y in this case. So now y prime will be the application of the function fr onto y. So far so good? Any questions? So the first step is that we're going to add nodes, extra nodes in the control flow graph for those functions, for the start and the end, for the call site and the return. And then just keep adding connections between every call site to the beginning of the caller, the callee method, or the method that's being called, so the caller, the callee, and from the end or the end point of that callee method into the return, back to the return site. All right. So what is the difference really between inherited and synthesized analysis information? Is as follows. So inherited analysis information, or the input facts, it gives you information about formal parameters and global variables. And global variables is an important aspect of it. I mean, formal parameters is kind of obvious because these are the arguments that are being passed from the call site to the method itself. So it's obvious that we can see that. But there is also the global state of the program. So these could be global variables in terms of C and C++. These could be static fields, public static fields in terms of a language like Java. Any variable that could be that is globally accessible beyond the method boundary should also be part of that fact that you are passing along to the function, because that may be used in computations inside the function, or may be modified even inside computations of that function. Particularly, we are interested in knowing like which variables may hold constant values, or for example, we might be interested in knowing which variables may hold constant values, or which variables alias with each other, or which locations can a pointer point to at runtime. Can a pointer variable point to? All these informations could be one of two things. It could be a may information, it could be a must information. Must information means it's going to be flow sensitive. May information means it may or may not be flow sensitive. It may be flow insensitive or flow sensitive. For the synthesized analysis information, we're basically answering, or that part of the analysis is answering what will happen for the side effects of the procedure call. So when we call a method, what are the side effects of that method? How would it affect the input facts? Again, this is very similar to the monotone framework. If you recall from our first two lectures of the course. In particular, we might be interested in something like which local or global formal variables are defined in a callee, in a method, as in defined as in having values in them. Which variables might be used? So a liveness analysis, a live variable analysis, and so on. Again, this information that the analysis is computing may be, could be a may analysis or a must analysis. So now that we have seen those connection points at the beginning and the end of the method, and at the call site and at the return site from a method call, now we are moving on to create what we call the inter-procedural control flow graph. So from the name of it, it is some form of merging the control flow graphs of various methods together using that method that we just described. So how are we going to do that? Sometimes in the literature also, this ICFG, or inter-procedural control flow graph, is called the program supergraph. We're going to see later on in IFDS that there is a variation of that called the exploded supergraph. So hold on that thought until we talk about IFDS. So if this is going to be our procedure space, so how are we going to create this ICFG or program supergraph? So let's say we have a main method. So we're going to have sMain, the starting point of main, the end of main. We're going to have method P, so we have SP and end of P. We're going to have a method Q, so we're going to have SQ and also EQ. Then we're going to have, those are the starting and the end points of every method. Between those start point and end point, we are going to have the regular control flow graph for that method. So we have now in front of us 3 different control flow graphs, one for each method that we have in our program, one for main, and one for method P, and one for method Q. Now it's time to merge them together. So how are we going to merge them together? Well, let's see. First, we need a call graph, because without the call graph, I don't know which call sites I have, which methods or target methods these call sites may dispatch to. So the first thing I need to have is my call graph. So assuming that I have this call graph here, so the main method calls P calls Q, and Q calls P back, right? So how I'm going to do that? Well, I'm going to introduce two things, like I said, in like 2 minutes ago or 3 minutes ago. For every call that I have, so if I go back here, so see here, call P, call Q, call P, call P. For every one of these call nodes that I have in my control flow graph, I'm going to replace them with two nodes. One is going to be for the call site, and I'm going to give it a label. So I'm going to call P at C1, I'm going to call Q at C2, call P at C3, call P at C4, and I'm going to have a corresponding return site for it. R1 for C1, R2 for C2, RC for C3, and R4 for C4. And now I need to connect every call node to the start point of the corresponding method that it dispatches to, and the return of that method, the end of that method to the return site of that same calling node. So here in this case we have call P, I'm going to connect that to P. I am going to see the end, connect that to R1. And the same thing for Q, I'm going to connect that to SQ, and I'm going to connect the end to R2. Same thing for these calls to P here, I'm going to connect C3 to calling P, and I'm going to connect the return or the end of that method to R3, and same thing for the last call that I have in my program, which is call P here on that side here. I'm going to connect that to SP and the end of P to R4. So far so good. Any questions? All right. All right, it's all good then. The second thing is, so now that I have all these caller-callee relationships, the next thing that I need to do is I need to figure out how am I going to navigate this ICFG. So there are many, many different paths in there, but I need to figure out, are there any paths that are invalid or not? This again goes back to when we talked about realizable paths and valid paths, when we talked about the monotone framework and how we go through the control flow graph, and there might be some paths that are an over approximation of the actual runtime behavior of the program at runtime. So one thing that this ICFG can give us is valid and realizable paths. So a valid and realizable path would be the following. Always start from the main entry point of the program. Does this diagram have a special name like CFG or Hasse diagram? No, the Hasse diagram is only for lattices. CFG is the control flow graph. This is called ICFG. So an I for inter-procedural, CFG is for control flow graph. So it's an inter-procedural control flow graph. All right, good. So the thing that we are interested in knowing here are valid and realizable paths. So how do we know those valid or realizable paths? Always start from the entry point of the program. In this case, it happens to be smain, but it could be anything, whatever it is, depending on the language that you are analyzing, the type of programs that you're analyzing, and so on. So here it is going to be smain. A valid path would be, well, I'm going to call A plus B, right? I'm going to execute A plus B. And then what will be the next step? What will be the next node that I can visit from this point on? That's an easy one. It's going to be C1, right? There is no point, there is no other node in the graph that I can go to except C1. So I'm going to call P, C1, and then what will be the next node that I execute? Again, this is going to be an easy one. SP, right? I'm going to call the function SP, so I'm going to go to SP. I only have one outgoing edge again here, so I'm going to call Q, which is C2. Now, where am I going next in the control flow graph, in this path? Again, SQ. I only have one way to go next, which is SQ. So now what do I do? Which path should I take? Who knows? Exactly. Who knows? Like, I don't know at this point what exactly the runtime behavior of the program is. So which path would you take? You need to pick a path, right? Because you're trying to find valid or realizable paths. Which path would you take? Start to EQ. Okay. Why did you pick that path? Straight, shortest. To make this path valid, this is going to be the shortest path basically that takes you there, right? That's one way to look at it, right? Because I can pick whatever path I want, so I can take this path, so I can go there to EQ. It's a valid path. Then what happens after that? So EQ, where should I go next? R2 is the only way to go, right? There's only one outgoing edge from EQ. So the here in this control ICFG or inter-procedural control flow graph, I can only go to R2, and then from R2 again, I only have one way to go, EP, and then from EP, where do I go next? To make things simple, let's go to R1. All right. So why are you saying to make things simple? How can it be complex or more difficult or worse than just going to R1? I can see recursion other ways. Sorry, I didn't get that. What do you mean by recursion here? It will be invalid if you go to R3 and RQ and R4, right? I mean, P calling Q and Q calling P. Okay, so both are correct. So the thing that we should notice here is, even though the two paths or the two edges or the three edges that are coming out of P, so there is 1, 2, and there's 3, those 3 are valid on their own, right? These are potential edges that may happen at a given path at runtime. However, it is not enough at that point, without extra data structures and extra information, to say, at this point, where should I go back to? Should I go back to R1? Or should I go back to R3? Or should I go back to R4? Unless I remember that at one point, I took C1. I'm coming here from C1, right? C1 given the call site C1. And that should tell me that I should return back to R1. So let's have a quick question here. What is some data structure or some mechanism, if you remember your 229 course or your computer architecture course in assembly maybe, or in other languages, that allows you to remember where you are coming from? At a given program point, how did you arrive to that program point? Is there any data structure or any concept that you remember from your previous courses that helps you to do that? Do you mean stack? What kind of stack? Call stack, exactly. That's exactly correct. So it is the call stack that allows you to do that. So assuming that we have the proper call stack, it will tell us that at one point in the program, we are at this point in the program or at this point in the ICFG because we are calling P from C1, and whenever we have a return point, we have to return back to R1. Not to any other return site, because once we return, we need to go back to R1 before we go elsewhere. Otherwise, we're going to mess up all the calling relationships. So here, we're going to go back to R1, then we're going to go back to main. But to be able to do so, we need to have a call stack. We need to maintain a call stack. So the ICFG would have to have a little bit extra help there so that we can actually do this properly. So how are we going to maintain a call stack? Well, it's just a stack of method calls that we're just going to push on the stack whenever we have a method call. Whenever we return from a method, we're just going to pop it off. It's very simple call stack. In this case, when we call the main method, we're going to add the main method. We're going to push it on the call stack. Whenever we're calling P, we're going to push P on the call stack. And here's the way we're going to push it. We're going to push P, but we're also going to push which call site? It's too many. Which call site specifically we are calling P from? Because we may be calling P from different call sites. So we don't want to mix them up as well. We want to be able to differentiate between calling P from C1 versus calling P from C4 or C3. So we're going to push P colon C1. Just a label that says I'm calling P from the call site C1. And then I'm going to go ahead. Maybe at this time, I'm going to call P. I'm going to go to SP, then call Q. Then call Q goes to SQ. So now I know that I'm calling Q from call site C2. So I'm going to push Q colon C2 to my call stack. So my call stack is growing as I go. And then I'm going to go to Q. I'm going to go back to EQ at this point. Now I'm at an end point of a control flow graph of the method. Or I'm at the end point in general, because it doesn't matter which part of the control flow graph it is. As soon as I'm at an end point, that means I should be returning back to some return site. So which return site I should go to? Well, I'm gonna peek to my top of the stack and see, oh, where is the last call site that I was at? Well, the last call site was Q at C2, so I should return back to the call site that took me there, that brought me here, which is going to be R2. So I'm gonna go back to R2. And then from R2, there's only one way to go, which is EP. Again, here I'm at an end point or I'm at the end of a function in my ICFG. At that point, I want to go where to go next. So I'm going to look and peek onto the top of the stack. And I'm going to see that what brought me here was a call to P from C1. So I should go to the return site associated with C1, which is R1. So I'm going to pop off that method from the stack. I'm going to go to R1. And then at the end, I'm going to go to main. And that would allow me, or would prevent the algorithm from either going to R3, which is the wrong return point, or going to R4, which is again the wrong return point for my program. So basically, to be able to deduce this ability to return back to the right side, we need to also maintain a call stack. And here I'm going to return properly to R1. Then I'm going to go back to main. At the end, that's the end of my program. There are no outgoing edges, so I'm going to pop off main from my stack, and my stack is empty. And once my stack is empty, I know that I'm at the end of my path. So now I have a full realizable or valid path from the starting point of the program until an end point or a leaf in the ICFG, the control flow graph, the inter-procedural control flow graph. Any questions so far about this example here? No, I just selected it just because it was easier to show it on the slides. But if we go back, if we go back here, from that point. So assume that we are not going to take EQ now. We're going to go here. We're going to go to D equals A plus B, and then maybe we're going to go to call P. So at that point, we are no longer going to have QC2 as the top of the stack, but we're going to push to the top of the stack. What would it be? So P, C3, right? And we're going to go again to P. P is going to call Q. At one point, the recursion will have to return because Q seems to be a recursive call. So we're going to return back from, sorry, not a recursive call. Some sort of a mutual recursion between P and Q, basically. So Q is going to return at that point, or maybe it will take another branch, doesn't matter. So at that point, when Q returns here, it will, I need to show this. When Q returns in the second iteration, or in the second call, it will have to check first. The top of the stack is PC3. So at that point, it will have to return to, where would it have to return to? So it will go back to, oh, sorry. It will first have Q, C2. So then it will look at the top of the stack, which will be QC2. So it will return to R2, and then it will go to EP. But at that point, we're going to pop off this element from the stack when we return. Now, this blue element here will be the top of the stack. And at that point, when I'm going to be at this point here, and when I'm at this EP, I'm going to look at the top of the stack. It's PC3. So I'm going to go back to the return site that is associated with that call site, which is R3. And then I'm going to continue. So the algorithm will still be valid, and it will still follow a valid path. Does that answer your question, Mohammed? Okay, cool. So, moral of the story is, if you want to find the valid and realizable paths in the ICFG, you need to have something that maintains the call stack, so that you can navigate properly through any valid or realizable path in the program. Otherwise, your algorithm, your static analysis algorithm, will just compute spurious edges and spurious information that will generate false positives. So you will have a high rate of false positives. Your analysis may not scale because it's just exploring a way more paths that are not even valid or don't correspond to valid runtime paths that your program may have at runtime. All right, any other questions? All right. So how are we going to actually realize those changes here? So we're going to do that using how we can recognize those invalid paths. We're going to do that using a concept of called staircase of calls and returns. So what does that mean? So every call that we're going to have, it's equivalent to going one stair up in a staircase. So you're going one step up whenever you have a call. If you have another call, you're going one step up. If you have another call, you're going one step up on the staircase, and so on. Once you return from a call, it's as if you're taking one step down the staircase. So here this R4 would correspond with C4. And the return that you're taking on that staircase has to correspond to the last call that you have. So the last step down, or the current step down, would have to correspond to the last step up that you took. So R3 would be C3. Then you can have another call, right? So you can have after the return, you can have another call C5. But when you return, you will return back to where C5 is. You can have C4. You can call method. You can have the same call site again, C4. Then you can have C4 again, and so on and so forth. So this is what the staircase algorithm or the staircase notion would provide. Generally speaking, the way we're going to recognize invalid path is that every descending step must match a corresponding ascending step. So you cannot descend from somewhere if you haven't reached that place in the first place. You cannot go down from any point in the program, or you cannot go down from a staircase unless you have climbed the staircase to that point. That just doesn't make any sense, right? So you need to go there first to that point on the staircase before you can step down from it. That's what the same notion that we're going to use here to be able to understand what is going on. So, for example, I can keep going up. Even with that concept of the staircase of calls and returns, that every descending step must match a corresponding ascending step, there might be a couple of problems with that. So C1 might be calling C1, might be calling C1, might be calling C1. So you might get infinite recursion there. So not only that, but there are actually two main problems with this kind of notion. Problem number one, as I've just briefly hinted at with that example, is recursion. So what happens with recursion is the following. So if we follow this approach, we're going to have U as a call site, and I'm calling method P, so I'm going to go to SP, and then I'm going to call SI, and then I'm going to call SQ. I'm going through a series of calls, as you can see, from method P to method I to method Q to method J, maybe to method R, maybe to method K, and then back to method P. So these are the series of calls that I have. And maybe at one point when I'm at Q, I'm exiting the method Q, right? So once I'm exiting the method Q, I have to basically unroll my recursion in the same order that I had the calls into that recursion. So in other words, if you apply these calls F number of times, and you apply these returns G number of times, G must be applied the same exact number of times as F. You cannot apply G for 5 times when you applied F only for 3 times. That doesn't make sense. You cannot also apply G only for 2 times while you applied F for 5 times, because that means that you only unrolled back 2 iterations of the recursion, but not the 3 others. So you're stuck somewhere into your recursive call. And you cannot unroll G 5 times while you only had 2 times, because that means you somehow managed to come back from a deeper point in the call stack in the recursion than what you already entered into the call stack. So you called the recursive function twice, but you returned back 5 times. That cannot happen in practice. So the number G must be the same as the number F, calls and returns. But if you have that, you could have a prefix where G must be applied only at most as F. So you maybe have a fewer times of G. So instead of having the strict restriction that G has to be the same as F, maybe you would relax that assumption a little bit and then say, well, maybe for a specific prefix, I don't need to go through the whole iteration of the recursion, the whole unrolling of the recursion, and I'm willing to accept the fact that I returned only part of the recursion, while maybe I don't care about the others. So I'll give you an example. Maybe you are trying to over-approximate the behavior of some recursive algorithm. Let's see. Factorial, for example, finding the factorial of a value, right? Or the Fibonacci series. You don't want to go through all the recursive functions to calculate the factorial of a number, but maybe it's enough for you to figure out that maybe after the first couple of iterations, these are the kind of side effects that I'm interested to model anyways. I don't need to model all the way until I go to the end of the recursion. So this is kind of acceptable to do that. But the problem with this kind of abstraction, or the problem with this kind of compromise, is that you would need to find an accurate way of this over-approximation. Because you still, even though that you're not unrolling the recursion G the same number of times as F, the number of times you went into the recursion, you need to figure out a way that can soundly approximate, that can accurately approximate those number of iterations that were not unrolled, because they might be infinite. So you need to figure out an abstraction in your analysis that allows you to correctly and accurately approximate those values. We're going to talk about that actually more precisely and more thoroughly in our lecture on Tuesday next week. So hold that thought, and we'll figure out a solution for that next week. The other problem with this kind of staircase of calls and returns is that what if we want to do a demand-driven analysis? So what do I mean by a demand-driven analysis? So a demand-driven analysis is an analysis that starts at a given point in the program, pretty much similar to some examples that I showed you in our very first lecture, the introductory lecture. So you're typing up something in your IDE like Eclipse or VS Code, and you just want to know, for example, what kind of methods you can call on a given object. So you just press Control or Command and space, and it shows you a list of potential methods you can call. So what happens there is that given the current point, some demand-driven analysis just starts navigating through the program, starting from that point of edit or point of interest, to figure out what exactly are the methods that could be called given the current objects and their instantiations or potential instantiations and so on. So assume we have this piece of code here. You have a main method, generates some secret, calls foo, assigns some non-secret value to t, and then calls foo with t. And then what foo basically does is leaking that information. So let's say it just posts it to the web or something. So what happens there? So assume that we are searching from foo v. So we're searching from here, from that point. Right? So we're searching from basically the first statement of that method. And we're searching backwards to find all possible inputs to that method. So what happens there? So what happens is that we're going to have a return, right, RT. So we're going backwards to find, it's a backwards analysis, so we're going backwards. So we have a return RT, and we have basically the return is going to return here, and then we have a call site S, because we're calling S, and then we have a return site S. So that sort of defies our assumption that we need to have a balanced return. Every return you have should have a corresponding call site. But that is not the case, because here you have an RT, a return, that doesn't have any corresponding calls. So that tells the analysis, well, I don't know where I'm coming from or what brought me to that point. So I'm just going to assume, to be safe and to be accurate, to be sound, I'm just going to assume that I could have arrived here from any possible call site out there. So basically, you must return to all possible callers in this backward analysis. So to be sound, you have to assume that you either came from that point or you came from that point, which is not the most precise way to solve the problem, but this is the sound way or the accurate way that will not allow you to miss any potential runtime behavior of a probe. So these are the two problems with that staircase analogy that I used here. We're going to take a short break now, and we are going to continue at 1:20 p.m. Edmonton time. And after the break, we are going to discuss these couple problems briefly again, and we're going to see how we can actually solve these two problems together. So there is a magical solution that we're going to introduce briefly today in the lecture. And on Tuesday next week, we're going to talk about it a lot more, in a lot more detail, with its various approaches and various compromises and various trade-offs. So let's take a short break and resume again in about 4 minutes or 3 minutes. If you have any questions on the Zoom meeting, just type it up on the chat or use your voice chat if you prefer. I'll be happy to answer any questions. By the way, have you are you also experiencing dropouts or buffering on the Twitch live stream today as well? Okay. Yeah, well, the only reason I'm having it actually open is basically it's an. Maybe I shouldn't. The only reason I had it before is that I also am recording it so that it is a separate feed from our discussion here on Zoom. Uh, so it allows me to post things on the web without having any of our discussions, our private discussions in the class here on the Zoom chat. So I kind of like it that way. But I can also just not stream it and just record it pretty much the same way I'm doing it. But instead of having it on Twitch, I'm just going to record it. I guess it's doing a little bit better now, but it seems it's been having a bad day today. Sure, sure. Um, Sorry for what again? Yeah, right, right, right. Yes, exactly. Yes. Sorry. Go ahead. Yes. Yes, exactly. Yes, yes. So because when we are returning, so if we have, let's actually draw the CFG for this. So we're gonna have S. Oops. How do we do this? Let's remove all those. So here we're going to have S main, right? There is going to be a few things here. We're going to have C1 that goes to foo, and we're going to have R1, right? And then we're going to have more stuff. Then we're going to have C2 also goes to foo, and then we're going to have R2, and then we're going to have E main, right? Okay, and this is going to be S main. So here we're going to have S foo, and S foo is basically going to have, well, okay, C3 leak, and then we're going to have S leak, that basically just does something, and then basically just have E leak there, right? And then we're going to have R3, and this goes here, this goes here, this goes here, and I hope you can see now my writing on the white background, white text, sorry. This is E foo, right? And then e-foo goes to R1. This again goes here, and this also goes here, right? This is our ICFG. So now if you do it your way, which is the forward analysis, and that's absolutely fine, we're going to start from S main, we're going to go forward, C1, we go to S foo, and we have our call stack, right? So go to S foo, go to C3, I have leak, I can go back, I go to R3, I go back to E foo, and then I go back to R1. No problem, because when I'm at E foo, I'm going to figure out that I have a call site on my call stack called C1, so I have to return to its return site, so no problem. The problem comes from the fact that if I don't want to do a forward analysis, if I want to do a backward analysis, how do I know where to return to? So what do I mean by that? It means that I am basically here at, what would it be? I am basically at the end or the start of S foo, right? So if I'm here at S foo, or even worse, if I'm here at E foo, and I'm starting my backward analysis from there, like I don't know at that point, I don't have enough information on my call stack, and I don't have enough information that tells me where to navigate next in my ICFG. So the safest thing that I can assume is, I can assume that at that point my call stack would have either C1 or C2, and then I'm going to return my data flow to both of them, to both R1 and R2. Or rather, I would just go back, propagate, go backwards to both R1 and R2, and then propagate my data flow from there on. Because if I only propagate to one of them, I might be missing the other path, because I don't know which call site of these two brought me to that point in the backward analysis. So this is always a trade-off with a backward analysis. If you are starting at a point where you cannot, or you don't have enough information about which call sites brought you here, then the sound approximation, the correct approximation to do is to propagate the information back to all call sites. And you're going to see in maybe one of our papers later in the course that how this kind of approximation can make your analysis not scale, and what are the other workarounds that we can make that would make the analysis scale in this case. This one? Like here, basically, I'm differentiating. I'm differentiating the call sites with. This is the one where we call foo with T, and this is the one we call foo with S. But it could be RS and then CT and then RT. But I just use T first because this is my first call site going backwards. If I'm going backwards in the program. Does that answer your question? Okay, you're welcome. So we do have another question here, I think, or maybe a comment. I think the reason is that when you return from foo, you don't want... Yeah, exactly. You would have to assume that you came to that point in the program from any possible call site. So you have to find out first what these call sites are, and then propagate your data flow backwards to all of them. All right. So now that we have all these problems with recursion and with demand-driven analysis or backward analysis, the solution to all these problems is going to be, roughly speaking, context-sensitive analyses. So what is a context-sensitive analysis? Basically, it's a way or an approach that allows you to analyze the same method, but given depending on the context of the current call of that method. So we're going to enrich, again, our data flow that we're propagating from one statement to the next, which would affect how we define our flow functions in our analysis, with the context, with the information that describes how the call site is, or which call site that point in the program came from. How did I arrive to that point? And what is the information that may affect that describes the environment at that point of the current call. This is what a context is. So many considerations that we have to take into account when we define this context is, well, first of all, how we can differentiate between contexts. These are basically labels that have to be unique, so that I can tell if I see a label that, yes, this label means I came from RT and or CS instead of CT in the case of that demand-driven analysis that we just discussed. So I have to be able to distinguish or differentiate between different call sites. Also, if I have two different contexts because I have multiple paths or multiple call sites, I need to define a way to merge them together. So if I have two incoming edges or two different call sites that are coming to the same method, how can I merge the contexts and the information from one edge and the other, or maybe more of them? So first, you need a way to distinguish or differentiate between them. Second, if you have more than one, how you can merge them together. So there are different types of contexts that analysis engineers usually use. You can either have a simple call string that tells you basically the method call sites on the current call stack. So pretty much the call stack encoded as a string. That's what a call string is. So the way we're gonna, the other type of context would be a little bit more rich in the sense that it is a value that describes the input domain values as context. So instead of just saying, well, this is where I got here, depending on the call stack, basically encoding the call stack as a string, you have values that describe what is the input domain from your lattice that brought you to that point. Or alternatively, it could be some object context such that the currently executing object is the context that I'm going to use. So let's say you have some axis A.B.C.D.F, for example. Maybe I'm going to use my context as A.B.C.D, and then my method foo that I'm calling on this. Why is my pen not working? All right. Or it might be that I'm going to use the context as A.B.C along with foo. So I'm over approximating that actual access path here that I have. And there is many, many more types of contexts that we can use and can sort of define. Each one of them has its own trade-off between precision versus scalability versus performance of the analysis, as we're going to see in our lecture on Tuesday. Some other considerations that we have to take into account are important language features that affect the way we perform either inter-procedural analysis or context-sensitive analysis. First is recursion. We just discussed that because it may affect how we can define our inter-procedural data flow analysis. We need to have a bound computation and bound context. So that means you cannot let your context grow infinitely. You cannot also let your analysis run infinitely because it has to terminate at one point. So you need to have some model or some abstraction that bounds your computation somehow, that still can abstract what a recursion is, what a loop is, and so on. Typically, this kind of abstraction would use something that is flow insensitive for this over approximation, because if it is flow sensitive, it would have to model every single iteration of the loop or every single call and return of the recursion, because it respects the order of the instructions, and as if it does so, it would have to go on and on and on and on until the recursion is over. The second consideration is parameters and return values. So the first thing is, in our data flow analysis, inter-procedural data flow analysis, we should or must map the actual arguments to formal parameters and vice versa. And we shouldn't propagate too much information, because remember that all this information is going to be propagated with the analysis as we go. So think of this as the baggage that the analysis has to carry from one statement to the other. And the heavier the baggage is, the slower the analysis is. In many of the cases, in most cases, that would be the case, that the heavier the baggage, the slower the analysis. So I'll give you an example here. So in this example, we have a main method. We have a source of private information. We're assigning x to y. We're calling foo with x, and then we are going, in foo, we have just assignment b equals a, and then we're returning 0. So basically foo doesn't do much here. So at the call site here, we are only going to propagate to foo the facts that are relevant to it. So I don't need to tell it, for example, that y, I don't need to tell it anything about y. I don't need to tell it anything about source. I only need to tell it x. X is a private value because I deduced that already from the assignment to of source to it. So I'm going to propagate x, and I'm going to propagate that to a here. So at a given call, you only propagate the facts relevant to the callee and not all the facts that you have. At the return, you also only propagate facts that are relevant to the caller method, rather than everything that happened in the method foo. So here in method foo, you have a local variable b that you assigned a to, and b doesn't really affect anything outside the method. So it doesn't have any side effects outside method foo. So there's no point in returning by saying, oh, well, yeah, inside the method foo, b is equal to a. Well, that doesn't make any sense. So returning 0 basically means, well, this method is going to return nothing, so I can just propagate back the empty set. There's nothing really relevant to the caller that I need to return from that method. So one question that you should think about, and we briefly talked about that almost half an hour ago or maybe 40 minutes ago, is what do we do with static fields then? So what do I do with static fields? How do these static fields affect the current data flow? Would these be relevant or would these be irrelevant here? What do you think? Would you consider those static fields when you're propagating facts back and forth? Oh, sorry, I am not seeing. I had the chat scrolled up, so I didn't see the answers there. I think you have to, but maybe only if they are actually accessed in the given method. That's true. So again, but let's say that you are here at this call site, and at that point, before going to method foo, you need to make a decision whether you propagate the static fields or not. So you don't know what method foo is going to do with them. So what is the safest thing to do? What is the sound approach here? Would you propagate them or not? Yep, propagate them, right? So for static fields, just like we discussed a while ago in our lecture today, as you would do with global variables, you would need to propagate those values, because you never know whether foo would actually change any of those values or not beforehand. If you have a quick and easy way to figure out by maybe scanning foo for uses of static fields, then you would just propagate those facts beforehand. But if you don't know which fields it's going to access, then you have to propagate all of them, because then they could be changed or modified in that method, or could be used, and you need to model those properly. A few other things that you need to consider as well in inter-procedural analysis is aliasing, because these aliases might be created by callers and callees. So like in this case here, b.f.g is being passed along, A and B are passed to foo, and basically what happens here is that A is passed A is assigned to X, Y is assigned, A is assigned to X, B is assigned to Y. So here Y.F is equal to X.F, which means A.F is assigned B.F. So here, if B.F.G is leaked, that means A.F.G is leaked, which means it's going to be a taint that is leaked. You're leaking some resource. So the aliases might be created between the callers and the coolies. So you need to model aliasing and model aliases within either the flow functions or the context or the data flow facts that you're propagating from one statement to the other in the inter-procedural analysis. Virtual dispatch is another huge thing. You can have multiple possible targets per call site. Your call graph, you'd better choose a call graph that can accurately approximate those targets in virtual dispatch. You need to consider them all. You cannot just pick and choose because either you're going to pick fewer targets than necessary, so you're missing potential runtime behavior, or you're too conservative in your assumptions, so you have too many false positives and just doing redundant or unnecessary computations that you shouldn't be doing. Is your analysis doing this as a may or must analysis? Are you going to follow the flow? Are you going to be sensitive to the flow, the control flow of the program or not? And again, very similar to the intra-procedural branches at if-then-else constructs. So you need to merge facts if you have multiple targets, multiple targets for the call site. So you're going to merge the facts when you return back to where you are. Threads is another huge limitation or challenge that inter-procedural analysis and static analysis in general has to address, because if you look at intra-procedural analyses, those are typically sound even in a multi-threaded context or a multi-threaded execution. On the other hand, inter-procedural analyses are typically unsound if they want to be flow sensitive, because multi-threading basically says, well, I can be executing this statement here and then this statement here on two different threads, and this doesn't necessarily obey the order of the execution of the functions. So if you want to be sound and flow sensitive for inter-procedural analyses, that is not even possible. You would have to be unsound. So either you need to give up your flow sensitivity, and in that case you would have subpar results, or you just give up on soundness if you want to analyze a multi-threaded application. In general, if you have a flow-insensitive analysis, you're not impacted by multi-threading. And the reason is, in a flow-insensitive analysis, you just assume any arbitrary execution order of the function, of the statements in a function. And that basically means you can have multiple threads executing at any point in the program, and your analysis is just fine as it is. Usually, effective modeling of synchronization is a big research problem, and I encourage you to look up some of the literature of papers that are published at the main conferences in programming languages and software engineering, like in PLDI, POPL, ICFP, eCoop, FSE, ICSI, and so on, that are related to concurrency, either detecting concurrency bugs or resolving concurrency bugs, or just even reasoning about concurrent programs in general, not even just trying to fix and repair concurrency bugs. A major obstacle as well for inter-procedural analysis is library dependencies, because you typically have to analyze the application with its libraries. Sometimes it's too big to analyze, sometimes it's native code, not even in the language that your analysis is capable of consuming. So what do you do about those? The typical solution is you do some sort of handcrafted summaries. Wala, for example, the analysis framework Wala has some XML-based summaries that have been developed by domain expertise that model the data flow of methods in those native methods. Soot has a similar technique. FlowDroid also has a similar technique, which I don't remember if we discussed FlowDroid a while back. Maybe briefly mentioned it when I talked about Soot, when I talked about the intermediate representations and the difference between Java and Android. One other possible way is summarization or library summarization, and we have seen this in our CollGraph hands-on lecture when I talked about Averroes, but there is way more, a large number, of summarization techniques that are out there in the literature that other researchers have developed as well. One student in my group is also working on that, David Sikas. He's working on trying to summarize library dependencies so that we can scale up program analysis to large code bases. So to recap what we have discussed about today, or what we talked about today, basically context sensitivity analyzes methods multiple times. You analyze the method once, contextualize it or parameterize it so that you can apply a different context to it and then get a different result every time. And we're going to see later in the course, as in next week, how we are going to leverage that into having a more precise analysis. Challenges that face this are recursion, parameters, how we handle parameters, how we handle aliasing, how we can properly handle virtual dispatch, threading and multi-threaded executions, and also library dependencies. That's all I had for you today, for today's lecture. In our lecture on Tuesday next week, we're going to talk about context sensitivity and the various approaches, like specifically the functional approach and the call string approach, the differences between them and the trade-offs between these two approaches to support context sensitivity. And then we're going to start talking about another framework that is close enough in its notion to the monotone framework, but supports inter-procedural analyses called IFDS on Thursday next week. Thank you very much for today, and I hope you have a nice weekend. We still have a few minutes, so if you have any questions or you want to just hang around and chat, I'm happy to do that. Thank you.